Hello, my name is James Morris and I am a senior at Francis Marion University. I will be graduating in the spring of 2021 with a degree in physics and mathematics. I am doing my capstone project on the geometric multigrid method applied to differential equations. So to start with, I'll be looking at the matrix equation AX equals B and how it can oftentimes be more useful to approximate the solution to this equation whenever your matrix sizes get large. So typically, doing a direct solve is done by applying the inverse of the A matrix to both sides, providing you with a solution. However, taking the inverse of large matrices is pretty computationally heavy and not typically the most efficient thing to do. So another option is to use an iterative solver and use that with anywhere from 100 to 1,000 or more iterations to approximate the solution to this matrix equation. While it can be done, again, it errs on the side of being computationally heavy and not the most efficient. So that is where the multigrid method really shines, and that's what we will be talking about further into this project. But to start with, I'm going to show you how this can be solved, or partially solved, with just an iterative method such as weighted Jacobi. So if we look down here, it's a little bit hard to see, but we have an equation. It's just a sinusoidal equation that is based off of modes, meaning we can pass in different modes. In this case, we have 1, 3, and 6, where 1 is a low frequency, 3 is a mid frequency, and 6 is considered to be a higher frequency. But to actually evaluate this equation, we first have to get it into matrix form. So to do that, we're going to use the finite difference method, which is just a tridiagonal matrix of 2's and negative 1's, where 2 is on the main diagonal. Okay. So to start with, we're just going to plot our equation. So here we have, in blue, we have this low frequency mode of 1 right in the center, and that's blue. And then if you can see it, there's this mid-frequency that does about 2 oscillations before it quits, and then there's a higher frequency in yellow that oscillates about this point. Okay, and if we look to the right, we have the error reduction as a function of iteration number for the weighted Jacobi method. If we look across the top, we can see that the error reduction is almost none for low frequency error. And if we look in the middle, for the red curve corresponding to the mid-frequency error, it is reduced by approximately a half, but again, that is not very good. And then if we look across the bottom, that high-frequency error is reduced almost completely, which is great, and that leads us into the multigrid method. So what the multigrid method is doing, essentially, is taking your low-frequency error, zooming out, and then giving it the appearance of high frequency error, and then solving on that high frequency error, and then zooming back in where it just looks like a solution. So with that being said, we can talk about prolongation and restriction and how they are able to convert domains to do these different mesh sizes. Okay. So if we look here at the bottom, we have an example of prolongation where we go from a coarse grid to a fine grid, which is typically done at the bottom of a V-cycle moving back up when you want to push it up to a higher domain. So all that's doing is interpolating values on the coarse grid and moving them down to the fine grid. And then on the restriction, all it is a weighted average that typically starts at the top of a V-cycle and pushes its way down to the coarse. And it just takes a weighted average of a center value and another value on each side of the value in the middle. Okay. So with that being said, we can look at how the multigrid is actually able to reduce this low frequency error that we couldn't reduce before. We're going to look at this new equation, and that is plotted here. This is the original error function. And if we run through our first iteration of multigrid, our first restriction, we notice that it gets reduced a little bit, but it's not super obvious. And I will mention that we're on the same range and domain. So typically whenever you run through multigrid, your domain changes, but I set our domain to be the same all the way across, so it would be easy to compare. And if we look at the second restriction, we notice that the error is reduced significantly. All that's left over is this low frequency error, which is what we would expect to see on the previous section. Running one more restriction, we get almost zero error, which is ultimately what you would want and would provide a good enough solution. And then all you do from there is prolongate back up to the original domain, and you have your solution. Okay. So using these methods mentioned before, we can extend this to a model problem. And for our model problem, we will be looking at the steady state discretized heat equation, where the equation for that is represented here. That is minus the gradient, dot product with K, which is the heat conduction coefficient, times the gradient of U, which is the temperature, equal to some function of a heat source. Okay, this can be expanded out to yield a matrix equation, where K represents the A matrix, which is necessary for us to apply an iterative method. In this case, we're going to use successive over relaxation to do our iterations. It converges a little bit faster. I'm not going to go really far into depth on how that one works. Just know that it converges quite a bit faster than weighted Jacobi. Okay. So here we can produce this image of this discontinuous heat conduction coefficient. So this is a disk where half of the heat conduction coefficient is lower than another half. So there's that jump discontinuity between those two places. It is heated from the top. So notice that on the back side, height and color represent temperature. So on the back side, that heat conduction coefficient is higher, which is expected, than it is in the front. Okay. So the geometric multigrid method is extremely useful when reducing large amounts of error. It is not completely necessary with small matrix systems, but whenever you move into larger systems of equations, it can be extremely useful. I would like to thank my advisor, Dr. Brauss. Without him, this project would not have been possible. He provided ample knowledge of the subject and was able to guide me through any and all questions I had. I would also like to thank Dr. Dungan, as he provided quite a bit of help with regards to the project as far as what path I should take as far as complexity goes, because PDEs are typically more difficult. I started with a PDE and ended up just on this differential, this one-dimensional differential equation. So he really helped guide me in that aspect. But that is all I believe we have time for. Thank you so much. Y'all have a good afternoon.